All right, let's just dive right into this explainer and completely demystify the classic jump to the end array coding problem. If you've ever literally banged your head against the keyboard trying to figure out messy, pathfinding algorithms, well, you're absolutely in the right place. Today, we're going to flip our intuition totally upside down. We're talking about a solution so elegant, you'll honestly wonder why you didn't think of it first.
So here's our quick roadmap for this explainer. First, we'll define the jumping problem, then look at the dead-end trap. After that, we'll try thinking about it backwards, step through the actual solution, break down the greedy choice property, and finally, wrap up with an algorithm complexity analysis.
All right, part 1, the jumping problem defined.
The setup here is, well, it's deceptively simple. You're given an integer array, and you always start at index 0. Every number you land on represents your absolute maximum jump distance from that specific spot. And your one and only goal? Just determine if it's possible to reach the end of the array. That's it. It's a straight-up true or false question.
Now, if the array was just packed with positive numbers, solving this would be a total breeze. Take the array 3, 2, 0, 2, 5. Starting at index 0, which has a 3, we can easily jump 3 spaces over to index 3. That spot holds a 2, which carries us the rest of the way to the final index. Boom, success.
But, of course, it's rarely ever that easy in interviews, right? Moving on to part 2, the dead-end trap.
The true villain of our story here is the 0. When you're trying to jump forward, hitting a 0 is a literal dead end. Let's look at a new array, 2, 1, 0, 3. If you jump from the 2 to the 1 and then from the 1 to the 0, well, you're stuck. A 0 means your maximum jump distance is 0. You can't move. It completely ruins that nice intuitive forward path we just built.
So the natural question is, how do we guarantee we avoid these dead ends? When you first see this, your brain probably immediately jumps to the complex stuff. You might start sketching out massive recursive trees to check every single combination of jumps, or maybe try to wire up some heavy, exhaustive pathfinding algorithm to map out the safe routes. But honestly, there is a much, much more elegant way to handle this.
Which brings us to section 3, thinking about it backwards.
There's this fantastic piece of advice from the source material. Let's think about this problem backward. Our destination is the last index. So here's the absolute game changer. Instead of pulling our hair out figuring out how to get from the start to the end, what if we just pretend we've already made it to the end? Think about it. If we can reach the final index from the space right before it, then that earlier space just became our brand new destination.
Let's visualize this. Take that winning array from earlier, 3, 2, 0, 2, 5. The final spot is index 4. Let's just drop a marker right there and explicitly declare destination equals 4. By starting at the very end and simply checking if we can reach this spot from just one step back, we simplify the logic so much. We literally do not care about the whole path anymore. We only care about the single step immediately in front of our destination.
Okay, let's see this in action. Section 4, stepping through the solution.
Look at the incredibly simple math that replaces all that nasty recursion. We're stepping back to index 3, which holds a value of 2. We just add the index number itself to its jump value. 3 plus 2 is 5. Is 5 greater than or equal to our current destination of 4? Yeah, it absolutely is!
And because that basic math works out, our destination marker leaps to the left. We update the variable. The new destination is now index 3. Take a second to realize what we just proved here. If any number on the left side of this array can just manage to reach index 3, we have mathematically guaranteed they can reach the end of the array.
Let's step left again and see what happens when we hit a trap. We arrive at index 2, which is our dreaded 0. Run the formula. Index 2 plus jump value 0 equals 2. Is 2 greater than or equal to our new destination of 3? Nope, it falls short. And because it can't reach the destination, the marker just stays exactly where it is at index 3. We literally just ignore the dead end and keep moving backwards.
So we step left again to index 1, which holds a 2. Index 1 plus jump value 2 equals 3. Is 3 greater than or equal to our destination of 3? Yes, it is a perfect match. That means from index 1 we can successfully bridge the gap right over that dead-end 0. Our destination marker shifts left once again, making index 1 the new target.
Finally, we're all the way back at our starting point, index 0, which holds a 3. Index 0 plus a jump distance of 3 gives us a maximum reach of 3. That easily clears our current destination of 1. So we make our final update, shifting the destination marker all the way to index 0.
And here's the grand finale of the whole thing.
After iterating backwards through every single number, we just check one final condition. Does our destination variable equal 0? Since our marker successfully made it back to index 0, the code just returns true. We definitively proved a valid path exists, and we did it without ever mapping out the exact path itself. How cool is that?
Let's dig into why this works so flawlessly. Section 5, the greedy choice property.
Imagine a scenario where multiple different initial jumps can all reach an eventual destination way out at index 7. Now, what happens if we shift our destination left to an intermediate valid jump, say index 5? By comparing these paths, a really crucial truth emerges. Any index capable of reaching that far destination at index 7 can definitely reach the very first valid intermediate destination we hit at index 5. The jumps just overlap it.
And this completely nails why this is a textbook greedy solution. A greedy algorithm makes the best, most immediate choice at each step, what we call the local optimum, hoping it leads to the overall global optimum. Because of those overlapping jump paths, the greedy choice property is totally satisfied here. We effectively simplify the problem at every single step backward, locking in a new destination without any fear whatsoever of missing a potential winning path.
Wrapping things up with Section 6, Algorithm Complexity Analysis.
Ultimately, this all comes down to absolute efficiency. By ditching forward pathfinding and that memory-heavy recursion, we achieved a time complexity of big O of n. We only iterate through the array exactly one time in reverse, and honestly, it gets better. Our space complexity is a constant big O of 1. We aren't building giant arrays of paths or calling massive call stacks. We're literally just storing and updating a single destination integer variable in memory. It really doesn't get more optimized than that.
I really hope this explainer has totally changed how you approach coding dead ends. By simply flipping the script and making the destination our starting point, an incredibly difficult pathfinding problem just melted into a trivial math equation. And it leaves you to wonder, what other seemingly impossible, overly complex problems in your code or even your life can you solve just by working backwards? Keep that in mind the next time you hit a wall. Thanks so much for learning with me today.